Hello everyone, myself Shashank Prashar and I am currently working as Associate Staff Engineer in System Software Team in Samsung Foundry Business at Samsung Semiconductor India R&D. Today I'll be presenting on the topic Proposal for I3C Support in Zephyr RTOS, and also I'll be speaking on behalf of co-author of this presentation, Yeeun Kim as well. So let's get started. So these are going to be the presentation topics. First of all, we are going to have an overview of I3C, as this is comparatively a new protocol. So it's possible that some of you might not be totally aware about this. We'll be starting with brief introduction to the I3C protocol. Then we'll be covering the features that this new generation protocol is offering. Then in the next section, we will see why we are trying to bring spotlight to this I3C protocol. Although Zephyr already has support for certain communication protocols. Then in final heading, we'll be proposing the software for I3C, and we'll be going through the file structure of the software that we are proposing. Then we'll be understanding the probing sequence of I3C in Zephyr. After that, we will check out the data transfer sequence for this communication protocol. So yes, it is going to be quite informative and exciting to know about this new guy in the market. So let's get started. I3C protocol. So I3C is the new industry standard that recently got released in 2016 by Mobile Industry Processor Interface Alliance, also known as MIPI Alliance. I3C interface is very similar to I2C interface, but still it's much more advanced. The additional I stands for the keyword improved, stating I3C's improved version of I2C. So just like an I2C interface, in case of I2C, it has an open drain data line called the SDA line and the push-pull clock line, SCL line. The open drain or the open collector SD line allows the slave to take control of the data bus and initiate interrupts. And the push-pull SCL line is used by the master to clock the communication bus up to 12.5 megahertz of max clock rate. There is availability of in-band interrupts that not only allows slave to initiate communication, but also allow devices to hot join as well. It also supports dynamic and directed command codes, so hot join devices can be assigned addresses dynamically. I3C supports multiple classes of devices, including main master, secondary master, I3C slave, and I2C slave. Master can dynamically assign 7-bit addresses to all I3C devices, while supporting the static addresses for legacy I2C devices. So, if we move on to the next slide. I3C features. So what are some of the key features? Why do we believe I3C is such a great interface? First is it's a fast and efficient communication channel. It's a multi-drop 2-wire interface with the 12.5 megahertz of max clock rate, and different voltages are supported from 1.2 volt to 3.3 volts. With the I3C basic, that is the free version, it supports up to 1 volts. It also allows dynamic switching between push-pull, pull-up, and high-Z configurations, so that we can have best of the efficiency for each scenarios. There are line codings now. No more just standard data rates, but high data rates are supported as well. So I3C, unlike I2C, is not just a normal bus. Now it supports advanced functions as well, like in-band interrupts, device resets, hot joins, error detection routines, etc. That is all things that are needed in today's embedded ecosystems, right? On top of that, now we have system management options. That is, we have the option for primary and secondary controllers. There is dynamic address assignment. Also, there is DCR, BCR configuration registers. That is, DCR stands for device configuration register, and BCR stands for bus configuration register. These registers allow more usability and management for the system designers, basically. So, and just to add again, there is backward compatibility for I2C. There exists different bus operations for I2C only, for I3C only, and there is mix of I2C and I3C devices operation. So for those who are still using legacy I2C devices, I3C is a compatible controller. There is basically a 50 nanosecond spike filter which makes fast data rate operations invisible to slow I2C devices on the same bus. So that is all for I3C features. If we move on to the next slide. So here we can see the comparison between I3C, I2C and SPI. So we can see in case of I3C, we primarily need only two wires, SCL and SDA. But in case of I2C, we require separate interrupt lines for each slave because inbound interrupts are not present in case of I2C. And in case of SPI as well, we will require separate interrupt lines and separate select lines for each slave. So as the number of slave devices increases, the complexity of the system will increase as well. This we can witness in the next slide. Let's move to the next slide. So this is typical I2C and SPI host sensor system. Here if we look, we can see a typical embedded system where multiple I2C and SPI sensors are connected. If we generally think, say about our smartphones, we can see there can exist accelerometers, magnetometers, gyroscopes, NFC sensors, etc., which might be using I2C bus. Where we can find apart from SCL SDA, there is presence of multiple interrupt lines and synchronization lines for which separate GPIOs might be required. Similarly, if we look at fingerprint sensor here, ADCs, touchscreen display sensors, these all are implementing say SPI. Apart from interrupt lines, they are requiring separate select lines as well and other lines, etc. So as the count of sensors increases, these interrupt lines, synchronization lines, and select lines will also increase, making the system very complex because of large number of input outputs. Right. Also, from analysis of this, we can tell these require separate interfaces for I2C and SPI, resulting in overall fragmented interface. Right, for which we cannot have a standard driver for host. So we can see how complex a system can get with current software support in Zephyr. If we move on to the next slide. So here we can see if we implement I3C on same system, then overall package size is decreased. The system is looking much more complex. When using I3C implementation, it takes goodness of both I2C and SPI without increasing the overall complexity. On top of that, we get advanced features like IDIs, which are compensating for any extra interrupt lines, just as we saw in the previous slide. And we have dynamic address assignment and overall higher data rates. So that too by just using the two SDA and SCL lines. No extra lines are required in this system. So we can see that how simpler the system can look with the I3C software support, right? So if we move on to the next slide. Proposal of I3C drivers for Zephyr. So looking at analysis and conclusion in above slides, it is quite clear to all of us that all those factors inspired us to bring I3C to Zephyr. Thus, we'll be proposing the software support for I3C master driver for Zephyr. The code written is inspired from Linux kernel, and all of the driver working has been verified with the I3C states using Zebul emulation platform for testing and validating. So if we move on to the next slide. I3C software file structure diagram. The diagram here depicts the relation between the master driver, master core, I3C interface, and the linked header file. The blocks in red and blue represents the structure which is our implementation. The blocks in gray represent the software part that is not being proposed, and the blocks in green represents the hardware portion for better visual understanding of structure. So, the flow starts from the top. The user application accesses the user interface, which in turn accesses the I3C related APIs via the I3C.h header file. This header file further accesses the core file for exposing driver operations to user. The core file here contains the helper functions and structures to support the I3C master driver. The corresponding header files like I3C dw.h, that is master header, and master.h, that is the core header, are utilized by the master driver, as these header files contain necessary declarations and macros which might be required by the master driver. So this was the our I3C software file structure. If we move on to the next slide. Now let's get started with the I3C probe sequence. First of all, we have registered our probe function named I3C DW init to be called when drivers are called by their initialization priorities. This probe function gets called number of times on basis of number of instances we have for I3C master in our DT file. So a call by Zephyr RTOS to this probe function makes the system control to enter the I3C master driver. After entering the init, first of all, the address slots that are available for being used during dynamic addressing are initialized. Not all address values are available for use. Many of them are reserved addresses that the I3C uses for other purposes. This is taken care by I3C bus init address slots function. When we say address slots are initialized, we simply means they have been marked as available or reserved for usage during dynamic address assignment of found I3C slave devices. Once the address slots array has been initialized, the control moves out of this function. Then control enters into define I3C bus mode function. As the name suggests, this function is used to select the bus mode of operation. Depending on address slots initialized, we know what kind of slave devices our driver will support. I3C bus mode can be pure I2C bus mode, pure I3C bus mode, or can be mixed bus mode where both I2C and I3C slave devices can be present. Once this is done, the control moves out of this function, and then control enters into DW init SCL timing function. Here again, as name suggests, all configurations related to timing parameters are taken care of. The bus mode of operation and type of slave devices present may influence the timing parameters being used during I3C master initiation. After this, control moves out to the master address config function, and here the configuration register responsible for assigning address to master device are configured. Also, the registers for deciding what kind of address will be used, that is whether static address will be used or dynamic address will be used for configuration, are selected here. After setting this up, control moves again out. Then control enters into the enable interrupt signal and stat function. Inside this function, before enabling the interrupt, the corresponding threshold values for command queue buffer and the RxJS data buffers are set, so that the interrupts can get triggered as desired values at desired values of buffer. Once these values are set, then corresponding IRQ lines are registered, and they are made to be bound with the IRQ handler using configuring IRQ function that gets called from inside of this function. Finally, before exiting, we enable the signals and their status corresponding to different interrupts set for the master controller. And after all the master configurations are complete, we enable the master controller. And at last, before exiting the probe, we call the dynamic addressing of attached slave devices. That is, after master is up, after enabling it via control register, because then only it will be able to assign addresses to slave. So this will be called at the end of probe once the master has been enabled. If we move on to the next slide. So let's talk about some of the important structures that are used at different steps of probe. When Zephyr probes, the I3C master driver this DW I3C config structure is filled with data from device tree properties, that is from a master instance for each master instance. This structure basically holds the I3C master basic configuration data. Here the structure members are uh, core clock. This variable holds the device core clock value that is currently being queried from device tree. Then we have the register variable. This holds the base address for the register address space of each instance. And then we have a max slave device. This is basically the max possible slave devices connection that is possible on the bus. And then we have command FIFO depth variable. This basically holds the depth of the command FIFO. Then we have data FIFO depth. This variable holds the depth of the data FIFO available. Then we have the configuring IRQ member function. This is this config IRQ function is used to bind or register the IRQ lines with the IRQ handler. So this is all about this structure. If we move on to the next slide, we can see after DWI3C config, the next important structure that gets filled is this DWI3C data structure. This again digs data from the device tree. So this structure is mainly responsible for holding the master's slave device info. Here the structure members are the base member variable. This structure variable holds data for master device. Then we have a free position variable. This variable keeps the index of the free address slots that are left in the address slot array after this after the dynamic address assignment is done. Then we have dat start address. This variable keeps the device address table start address. Then we have DCT start address variable. This variable keeps device character table start address. And then we have semexfer, which is basically a variable for semaphore for data manipulation. And then we have empty. This variable is basically mutex variable. Then we have exfer variable. This structure pointer holds data and related information for the data transfer operations. So this is all about this data structure. If we move on to the next slide. So after this is done, address slots for dynamic address assignment of slaves are initialized, marking them as free addresses on I3C bus, as shown in the code snippet screenshot below. This is the same what we earlier discussed in the probe sequence diagram. We enable the master, and then after we call this function for assigning the dynamic addresses to the slave from the address slot array that we initialized earlier. We move on to the next slide. Then we have dynamic addressing. So the flow diagram here explains the sequence of the dynamic addressing that is being handled during probe in our master driver. The I3C device configured as main master is responsible for performing dynamic address assignment of saved devices. In general, master will do this dynamic address assignment. In general, we do that when in one of the cases when the bus is getting initialized, and secondly when a new slave device gets connected. But currently, the second option is not supported in the proposed driver. Only the first option, when the bus is getting initialized, is supported currently. So we have two procedures to do DA. One is the set data procedure, which basically stands for a set dynamic address from static address. And this master assigns a dynamic address to any I3C device with the known static address using the directed specific command codes for set data. Secondly, we have ENTDA procedure. This is what our current driver is primarily implementing. It stands for Enter Dynamic Address Assignment. In this, master device assigns a dynamic address to any I3C device that is not assigned earlier any dynamic address. This is done using the broadcasted specific command code for ENTDA. The command code, when sent, gets a response from all the slave devices present. This includes a count of slave devices present along with the kind of devices present on the bus and what abilities they hold. So if you look at the sequence diagram here, when this dynamic address assignment function is called at end of row, it then further calls the master reset DA function. This function takes care of resetting any previous dynamic address assignments that might have done. So basically, it basically resets any dynamic addresses if any were initialized earlier. So to do so, it takes help of another function, this I3C CCC command init function. This function is used to initialize the common command codes for different purposes. In this case, for the resetting dynamic addresses. After this, the design where send CCC command function is called. This function uses another important structure called as the I3C CCC command structure. You can see it here. So this structure has members read and write variable. It tells whether master wants to read or write. Then we have ID variable. It stores the unique command ID for different commands. Then we have address variable. It holds the address of a target device or devices if it is going to be broadcast command. Then we have length variable. It tells the length of the command. Then we have a data pointer variable. It holds the command buffer. And then we have error variable. It basically keeps check for any errors that might get introduced during the operation. And once the structure is filled, then init expert function is called to transfer the command codes. After this, slaves are assigned dynamic addresses once they respond to the command with their each slave device sending their attributes to master for getting a dynamic address. So if we move on to the next slide. Now we'll talk about the I3C write sequence. The flow diagram here explains the I3C private write sequence that is currently implemented in proposed driver. So when user application using exposed APIs call the I3C write function, then in turn at driver end, this is what happens. So starting from the top, the DW I3C express function gets called. Inside this function, another important structure is filled. The structure name is DW I3C command structure. This structure has following members. So first of all, we have a command low variable. This variable holds the primary command, and then we have command high variable. This variable holds the secondary command arguments. These both are combined to form a specific directed or broadcasted command. Then we have TX length variable. This is the length of the data to be transferred, and then we have RX length variable. This is the length of the data to be received. Then we have error variable. This takes care of any errors that might get introduced during the transfer operation. Then we have buffer pointer variable. This holds the data buffer containing the data to be transferred. So after getting this filled, this init expert function is called. Inside this init expert, we set the data buffer threshold before filling the TX Then we call the function write TX data buffer that fills this the TX then after we will fill the command queue for sending the commands. Then data goes from TX4 to data bus. Then slave sends back response about data have been received successfully or not via this I3C DWIQ handler function, which in turn tells if it's a response interrupt from slave or not. Then in turn it calls the expert done function, which takes care of the transfer completion or if error handling, if any. So if slave says that the data sent is not of the mentioned length or some error happened, then master starts the error routine and retries sending the data again. So this is how the I3C write has been implemented in the proposed driver. So if we move on to the next slide, this is the I3C private read sequence. So we can see the flow diagram here explains the sequence of I3C private read that is implemented in our proposed driver. If we look at the sequence, we find that the sequence is very similar to the write sequence, but there exists some key difference. For example, the write tx data buffer function is not called prior to this enqueue command here. We get the previous slide. Here, this function was getting called in case of private write, but there is no such scenario in case of read sequence. Just command is sent telling the slave to send the certain data length to master. If slave is not busy, then it responds positively via response interrupts handled by this I3C DWIRQ function. Again, extra function is called to check the response. If no error bit is high, then this read RX data buffer function will be called, which will retrieve the data from the RX buffer of the master that the slave might have sent. So this is the sequence for I3C private read. The sequence is very similar to the write operation, but there were just minor differences that we highlighted. So if we move on to the next slide. So this was all on the topic proposal of I3C support in Zephyr RTOS. We went through the merits that I3C is going to offer, as now it has become part of Zephyr. We had quick walkthrough of the software file structure proposed, the probe sequence used in the master driver for probing I3C master, the read and write sequence implementation proposed in master driver. Apart from that, the code corresponding to shared software design is in process for mainlining. Also, other master features are already planned for porting to Zephyr, and our future plans for porting slave driver to Zephyr also exists. So I3C has a lot of scope in Zephyr that we will be witnessing in our near future from Samsung. Thank you. So, any questions?
Just relaying on for the people remotely, please type any questions you've got into the Discord channel. But one of the discussions that just happened in the room was we probably need to have a Discord channel specifically on I3C so we can all sort of thrash through and talk through this. There seems to be a lot of people that are interested in this topic right now and have partial works. So it seems like a ripe area for some collaboration and possibly additional meetings. Probably we can vector this through some of the other groups. I don't know. David, do you have ideas which ones might work for this? Okay. Yeah. Yeah. So possibly if there's a special interest group in a way we can sort of get people to register their interest possibly even in this Discord channel from the room right now, possibly set up an ad hoc meeting to discuss it further, or work from the dev meeting, I think you said. It might be a good spot to have further discussions too. Okay. Yeah. Right. So I think we can set it out of band or in the dev meeting, whichever seems most appropriate, and possibly create another action item out of this today right now is to create a Discord channel for I3C, so people wanting to collaborate on I3C drivers can have a place to hang out. Oh, I3C drivers. Yeah. Hey. Okay. Okay. Well, I think then, anyone else have any questions? Oh, Ryan just asked in the Discord channel, and how does the existing I2C driver interface with your I3C? So let's see if he responds. But I think we're getting close to time. We're at time right now, so we'll probably just keep the discussion going in the Discord channel, and I'll talk to Brett about creating an I3C Discord channel. Okay, thank you. And thank you very much to our remote speakers. Much appreciated.